You're watching the Argmin video channel, minimally valuable YouTube videos for frustrated mathematicians. I forget what I said in the previous ones, but let's go with that. This is the Real Analysis video series, lecture 11 on real vectors. So where we are in the course is we built up the reals in the first part of the course, then we looked at sequences and convergence, and then series and convergence. Now we're going to extend some of those results to the vectors. So as a recap of what you might already know, we have a vector space Rn which satisfies some vector axioms. I won't list them out here. You might have seen them in a linear algebra course. And they're defined as just x1 to xn, this n tuple, where each xi is a real number. And the properties of a vector space that we care about are addition. So 2, 1 plus 4, -3 is you add the 2 to the 4 to get the first element of the tuple, and the 1 to the -3 to get the second element in the tuple. Scalar multiplication, so say you had 3 times 1, 4. That would give you just multiply the first element with 3 and the second element of the tuple with 3. And this isn't true, or this isn't for every vector space. For Rn, it has the Euclidean norm. So x equals x1, x2 to xn. The norm of that is just the square root of the squares of each element, sum of squares. This is sort of related to a length. And you can think of it that way. You can think about distance between vectors. So say you had xy in Rn. The distance between them is just you subtract them off and then take the norm. And then that will look like just this minus y I. Whoops, the square is not supposed to be there yet. Square, and then you square root that whole thing. No negative. And it has an inner product. Defined as x dot y, or in alternate notation sometimes x, y. It's the dot product as another name for it. And it's just you multiply every element with each other, and then you sum up those resulting multiplications. Okay, so now note that if you take the inner product of a vector with itself, it's just, if you multiply xi with itself, that's just squaring it. It's right in the bounds, I equals 1 to n. And this is exactly just the norm of x, but squared. So this. And then we have the sum of squares, and there's no square root now, so that's why it's the squared norm. Okay, some properties that we're gonna look at or use. Property, this is the Schwarz inequality, or Schwarz, I mean to say, for all x, y in Rn. The absolute value of their inner product is less than or equal to x norm x times norm y. So let's prove this. I'm gonna write smaller just so I can fit it in. So 2 times the squared norm times 2 times the squared norm of x and y respectively, minus 2 times, whoa, I didn't mean to write that again, x, y squared. That is equal to 2, if you just expand out the inner product, you got xi squared yj squared, right? No, it's supposed to be xi yi, I believe. So it's the inner product squared for the norm squared of those vectors. So, and then you multiply them together. Oh, so you have all the cross terms. So it's just I and j minus 2, just these ones, and then you got, let's work with the other part for now. You can turn it into a double summation. Ij, so just every ij in the real numbers, if that's not clear. Or the natural numbers. Or not natural numbers, but in the set. So let's define n equals 1, 2, up to n. So this set. Just to make it less messy, I'm just gonna omit that part though. So then we have xi yi minus xj yj. And then we can take the summation to be common to them both. So then we have 2xi squared yj squared minus 2 xi yi xj yj xj yj, and then if you do if you expand things out, you get xi squared yj squared. If you split up that one and then put this in the middle and then put this other one, so there were 2, now there's 1 on each side, yj squared, right? And then if you factor it all out using what's it called? Well, it's a quadratic, you just use that. Ij xi yi minus xj y of j, and that's just greater than or equal to 0. So then if you rearrange things, you'll end up with the Cauchy-Schwarz conjecture, or the Schwarz inequality up there. Alright, so the next property is the triangle inequality. We've been using it sometimes for the proofs in the real numbers. Now we're gonna use it for this. For vectors, for all x, y, in Rn, the norm of x plus y is less than norm of x plus norm of y. And proof. X plus y squared is equal to the inner product of it, x plus y with itself, excuse me. And that's just equal to, so you multiply the x with the x, or inner product the x with the x, and the x with a y, so like FOIL, first outside, inside, last. And the inner terms, y, x, and then the outer terms, y, y. Now this is just x squared, and then you have two of these x, y terms, and then this is norm of y squared. And so by the Schwarz inequality, this is less than or equal to norm of x squared plus 2 norm y, or norm x, norm y, plus y squared. And then you do a quadratic factoring again, because these norms are just real numbers. Giving you this as required. Norm of x plus norm of y, and that's it. Or norm of that squared, norm of that squared, and if you take the square root, you get the Cauchy-Schwarz as promised. That's it for this lecture. We're going to be looking more, applying more analysis to these real vectors in the coming lectures.